And as we already know, convection, radiation, conduction, there is another mechanism listed in the lecture note, and it is a mixture of conduction and radiation. We call it contact resistance. Imagine we have two surfaces in touch with each other. And the temperature of surface A, let's say TSA, and in touch with the surface B at a temperature of TSB. The mechanisms of contact is pretty complex, as we see, because due to the surface roughness, besides the contact spots, there are also some gaps with some filler liquids, such as gas or fluid. So we have contact spots here. And also there are some gaps. So the mechanisms of contact is a combination given by the conduction within contact spots. For those filler fluid, it can be conduction or radiation when the temperature is super high. Because it keeps still within those gaps, so convection does not play a dominant role here. But it can also, the heat flux we use caused by contact can also be simply computed as a contact heat transfer coefficient times the temperature difference between those two surfaces in contact. It looks super similar to what we have learned last class, the convective heat flux. The H is the convection heat transfer coefficient minus the surface temperature, difference between surface temperature and that of outer flow. Here we have contact heat transfer coefficient times that the temperature difference between two surfaces. But as I just briefly explained there, the mechanisms is totally different. This is a combination of conduction and conduction or radiation. So it looks super similar, but they are completely not the same. The contact heat transfer coefficient for metal, it has an order such like 10 up-force watt per square meter per Kelvin. So don't get confused between those simple mass. We just use them to compute the heat flux or heat exchange rate with the given heat transfer coefficient. And we will spend the later half semester to learn how we can obtain those coefficients based on the geometry, boundary conditions, and surface properties, something like this. By now, we know how to apply those simple equations. That's okay. Continue with what we learned last class, the Fourier's law. We just assume the heat flows mainly in one direction. How about we consider in reality? How can we extend the Fourier's law into three-dimensional space? If we use the heat flux with a bar on top, it does not mean an average value, but it means a vector. Because the heat flux is, besides its magnitude, it also has directions. It can be up, can be down. can be sideways. So we use the bar to represent it is a vector. And similar like the 1D case, should times a minus K here, some more conductivity here. But how about the temperature gradient? In 1D, we have dt over dx for temperature gradient. How about for 3D case? If heat flows equally in x, y, z in 3 dimensions, you can represent things in 3, depose it into 3 directions. The bar over that also mean vector, and x, j, k are the unit vectors in x, y, z, the 3 dimensions. So the heat flux is a vector, and it has 3 components divided in the 3 dimensions. But in a mathematical way, we can represent this with a downward triangle. What's the name of that? It's gradient of the temperature. In 1D, it just dt over dx, but in 3D, it should be what's the difference between that strength D and this curvature here? Do you guys see the difference? Because in 3D case, the temperature now is a function of more than one independent variables. It's a function of x, y, z. So it should be a partial derivative. But if we assume heat flows only in one direction, it just is a function of only x. So it can be a total derivative. That's the main difference. And for this case, we assume K is constant for isotropic properties. Isotropic means the thermal properties are union in all directions. It's not a directionally dependent variable. But in reality, it's not always the case. For example, wood, it always conduct heat better along the grain direction, but not in the direction, the cross-sectional direction. So the more general way to represent Fourier's law, consider not constant thermal conductivity should be this is more general, as we can now capture the directional dependence on the thermal conductivity. But what we assume here makes the calculation much easier if we assume K is constant. It's not true, but the result we obtain with a constant K is almost nearly exactly the same.